So, like I said, we are actually, Section 3 of Quiz 3.2 is due tonight. And then I'm also going to be moving into Section 3.3. So we're a little bit ahead of the schedule, but you should have already done Section 3.3 because this would put us back on the schedule and stuff like that. So I'm going to finish up Section 3.2 today and move on into Section 3.3 before we continue on and get back into our regular schedule and stuff. So here we go. Now, remember the big deal about the Chapter 3 stuff. There's the Chapter 3.1, 3.2, which is review of exponential and logs. You were supposed to, and I'll just show you here, you were supposed to, for the Section 3.1, 3.2, Chapter 3 review of exponents and logs, you're supposed to watch the awesome video. And I actually went over and I actually produced these notes in our packet of notes and stuff like that. And you also had your WebWork stuff due on those exponentials and logs. But now what we're doing here is actually working on the calculus part of exponential and logs, which is honestly the limit aspect of this stuff. So just to remind you guys of some things that you were supposed to know to help you guys out with the old WebWork and stuff. This is kind of what we went over last time before actually spring break here. And that was this, these limit laws. Now, some of those limit laws you're supposed to know from Chapter 1. Things like this. What is 1 over infinity? When the denominator gets really big, so what is 1 over something really big going to go to? That goes to 0. Whether it be plus or minus infinity, when it's in the denominator, that goes to 0. Okay. 1 over 0 on the plus side, that goes to positive infinity. And 1 over 0 on the minus side actually goes to negative infinity. Some of the other things you were supposed to know. E to the infinity is infinity. E to the negative infinity is 0. And if you happen to have a base that is bigger than 1, a to the infinity is infinity, and a to the negative infinity is 0. However, if you have a fractional base, then a to the infinity would be 0, and a to the negative infinity would be infinity. So it depends on what the base is, whether it be a fraction or not. Some of the other things you were supposed to know. Let's see here. The tangent of pi halves from below, that's equal to positive infinity. The tangent of pi halves from above, that's equal to negative infinity. The natural log of infinity is equal to infinity. However, the natural log of 0 on the plus side is actually negative infinity. So all these are some of those limit laws that we were actually discussing actually before spring break and stuff like that. So, and last time we went over the idea of what the classic logarithmic graph looks like when the base is bigger than 1. Remember, you can't take the log of a negative number, nor can you take the log of 0. So you notice there's no graph over here. So starting from positive greater than 0, the graph shoots literally straight down, goes towards negative infinity. And the graph comes up and goes out and keeps on going forevermore. So the domain of a log graph is going to be from 0 to infinity. However, the range on any log graph is all real numbers, negative infinity to infinity. Just to remind you guys of some of the properties that we talked about. Logarithms solve for exponents, so they act like exponents. And so we have the log properties, and that is the log base b of m times n is equal to log base b of m plus the log base b of n. So a multiplication turns into addition. Similarly, division turns into subtraction. So the log base b of m divided by n is equal to log base b of m minus the log base b of n. And the log base b of m to the n, power raised to another power. With exponents, power to a power you multiply. So with logs, to multiply, the exponent gets to pop out front. So it's n times the log base b of m. And we talked a little bit about finding the inverses and using the log properties, and you were supposed to watch the awesome pre-section video to do these problems. And these are the limit laws we just discussed. Now remember, when it comes to logs, we're going to be focusing on two different kinds of logs. These are the log buttons on your calculator. The natural log, which is log base E, 2.71828, and the common log, log base 10, we just don't ever write the base on a base 10, so there it is. And when you take the limit, because of the graph here, when you take the limit as x approaches 0 from below of the natural log of x, the natural log of 0 from below, that goes straight down to negative infinity. However, the limit as x approaches infinity of the natural log of x is infinity. And it comes back to this idea, the natural log of 0 on the plus side is negative infinity, and the natural log of infinity is infinity. Similarly, whether it be natural logs or common logs, log base 10, the log of 0 on the plus side is negative infinity, and the log, understood to be base 10 of infinity, is infinity. That's what these limit laws are telling you right here. So, and I had a couple of problems on the old video here, but we might as well do one. And basically, the rule of thumb with these kind of problems is first rule of limits, plug it in. So it's basically it's chapter 1 all over again, except with these new functions. So here we go. What is the limit as x approaches infinity of negative 2 times the natural log of x plus 3 divided by 5? First rule of limits is plug in a number. This will be negative 2 times the natural log of infinity plus 3 divided by 5. The natural log of infinity, we know that to be infinity. So this will be negative 2 times infinity plus 3 divided by 5. Now you got to watch your signs and follow your nose. What's negative 2 times a positive infinity? That would make it a negative infinity. Negative times a positive is a negative infinity plus 3 over 5. Negative infinity plus 3. You got negative a billion plus 3, pretty much still negative a billion. So that's going to still be negative infinity divided by 5. And since 5 is positive, then negative infinity divided by a positive 5 would be negative infinity. Infinity on top, you get infinity, you just have to follow the signs. Negative divided by a positive is negative. Similarly, this problem here, take the limit as x approaches 0 on the plus side of the natural log of x plus 3x minus 2 divided by 4x squared minus 3. First rule of limits is plug it in. This is equal to the natural log of 0 on the plus side plus 3 times 0 on the plus side minus 2 divided by 4 times 0 on the plus side squared minus 3. Well, the natural log of 0 on the plus side, again, is one of those limit laws that we have memorized. The natural log of 0 on the plus side is negative infinity. So this will be negative infinity plus 3 times 0, well, that's still 0, minus 2 divided by 0 squared. 0 squared is still 0 times 4 is 0 minus 3. Cleaning it up, negative infinity plus 0 is negative infinity. Negative infinity minus 2 more is still negative infinity. Divided by 0 minus 3 is actually negative 3. But again, it's one of these problems where you kind of have to follow your nose and watch your signs. What is a negative infinity divided by a negative 3? Well, infinity divided by 3 is still infinity. I mean, you got $1 billion and you got to pay a third in taxes because of winnings or something or other like that. You're still pretty much rich, okay? So infinity divided by 3 is still infinity. However, watch the sign. What is negative infinity divided by a negative 3? What is that going to end up being? Positive. So the answer is going to be positive infinity at the end of the day. Does that make sense? So here's some more. What is the limit as x approaches 3 on the plus side of the log, understood to be log base 10, of x squared minus 5x plus 6? First rule of limits is plug in a number. So this would be the log, understood base 10, of 3 on the plus side squared minus 5 times 3 on the plus side plus 6. Let's clean that up. This will be the log of 3 squared is actually 9. Minus 5 times 3 is 15 plus 6. Okay. Now, 9 plus 6 is actually 15 on the plus side. Minus the 15 is going to give you the log of 0 on the plus side. And what was the rule about the log of 0? A log of 0 on the positive side, because you can't take the log of a negative number, where does it go? Classic log graphs look like this. And as you get close to 0, the thing shoots straight down. So what's the answer? Negative infinity. It's one of our log properties. What is the limit as x approaches 0 on the plus side of the log of the sine of x? Well, okay, go back to knowing your trig here. First rule of limits is plugging in. This will be the log of the sine of 0 on the plus side. Now, just to show you what's going on here, it's a sine graph. The sine graph starts at the origin, comes back out, back, and back again, and it waves forevermore. Here's 0. Here's the graph of y equals the sine of x. And as I approach 0 on the plus side, the sine of 0 is going towards what? The sine of 0 is what? Things we know from high school trig. Sine of 0 is 0. However, because we're approaching it on the plus side, the sine of 0 on the plus side is 0 on the plus side. So this will be the log of 0 on the plus side. And again, what's the log of 0 on the plus side? Just like in the last problem, things we know from limit laws, the log of 0 on the plus side is negative infinity. Now, pay attention to the next one, and then you're going to be beginning to see why these log properties are important. I want you to take the limit as x approaches infinity of the log of 1 plus x squared minus the log of 1 plus x. Well, first rule of limits is plug in a number. This would be equal to the log of 1 plus infinity squared minus the log of 1 plus infinity. Well, infinity squared is infinity, plus 1 is infinity. This will be the log of infinity minus the log of infinity. Well, the log of infinity by definition is infinity minus infinity. So what's the answer? Well, infinity minus infinity, isn't that 0? Well, sometimes, yes, but not always. It's called indeterminate. It depends on which infinity is bigger. If the first infinity is bigger than the second infinity, maybe the answer is infinity. If the second infinity is bigger than the first infinity, maybe it's negative infinity. Maybe they're the same sign. Maybe it is 0. Maybe this one is 45 more than this one. Maybe the answer is 45. It's indeterminate. You can't tell. So the trick on this one is this. Use your log properties. According to log properties, when I take the limit as x approaches infinity of the log of x plus 1 squared minus the log of x plus 1, when I subtract log, subtraction turns back into what? Division. So this will be one big log, log base 10 of 1 plus x squared divided by 1 plus x. Now, this goes back to chapter 1, dealing with our log properties. When you take the limit as x approaches infinity, or x approaches whatever on a log, or on any kind of function, you go after where the x is located at. The x is, my function is now inside this log guy over here. So this would be the same thing as the log of the limit as x approaches infinity of 1 plus x squared over 1 plus x. I'm just taking the limit where the x's are located at. Now right here, if I plug in infinity, I get infinity squared plus 1, which is infinity, over infinity plus 1, which is infinity. It's infinity over infinity. It's a different kind of indeterminate form. But if you remember when we had polynomials over polynomials, this is chapter 1.6 by the way, in case you wanted to go back and look at it. Chapter 1.6, when you got a polynomial over a polynomial, when you're taking the limit as x approaches either plus or minus infinity, you multiply by 1 over x to the degree of the denominator. What's the degree of my denominator in this problem? 1. It's 1 plus x to the first power. It's a degree 1. So this would be equal to the log of the limit as x approaches infinity of 1 plus x squared divided by 1 plus x. And I'm going to multiply by 1 over x to the degree of the denominator, which is x to the first power. So I'm going to multiply both the numerator and denominator by 1 over x to the first power. And I'm going to distribute. So this is equal to the log of the limit as x approaches infinity of, as I distribute, 1 times 1 over x is 1 over x, plus x squared times 1 over x is just x, divided by 1 times 1 over x is 1 over x, plus x times 1 over x, the x's cancel, you're left with just 1. Now, plug in your infinities. This is equal to the log of 1 over infinity plus infinity over 1 over infinity plus 1. Now, what is 1 over infinity? That was one of our log properties from chapter 1, way back when we used to do this kind of mess. What's 1 over infinity? When the infinity's in the denominator, what does those fractions go to? So these things go to 0. So you're left with the log of 0 plus infinity, which is infinity, divided by 0 plus 1, which is 1. So infinity divided by 1 is infinity, so I get the log of infinity, and that's one of our new log properties. What's the log of infinity? The answer is infinity. INF for you WebWork fans. Now, this next guy right here is one of these questions about inverses versus when it's actually a power of a function here. Okay? And just to remind you, anytime you got f of x is equal to y, this is equivalent in saying that x is equal to f inverse of y. This is what the inverse does. It takes the function and puts it on the other variable. So as f of x equals y, that's the same thing as x equals f inverse of y. So when they tell me that f of 3 is equal to 11, therefore, what can you tell me about what f inverse of 11 is going to be equal to? It's going to be equal to 3. It's the reverse of this guy. F of 3 equals 11. This is inverse. F inverse of 11 is equal to 3. These are synonymous. If you can go one way, you can go the other. However, this is inverse notation. This is power notation. This is f of 3 to the negative 1 power. What's f of 3? They told me f of 3 equals 11, so this is the same thing as 11 to the negative 1 power. But what is a negative 1 power going to do for me? Well, to get rid of a negative exponent, you put him on the bottom. So this turns into 1 over 11 to the first power. And anything to the first power is himself. So the answer is 1/11. Does that make sense? The difference between the inverse notation and the power notation.
Dr. Bailey,
Yeah.
for when you switch the log and the limit, was there a certain rule for that, or is that just something you can do?
Well, this one right here, going from limit of the log of this thing to the logarithm, this is called this is the property of limits.
Okay.
When you're doing limit problems, you take that limit as x approaches whatever, and you go after where the x's are at. Whether you got a function on the outside or inside, it doesn't matter. You're going after where the x's are at. So the ability to take the limit and put them on the inside of the log, that's because that's where the x's are located. They're inside the log, so the limit gets to go inside the log, and that's called a limit property. All right, here's another one from this particular section 3.2. Find the inverse function of the following. F of x equals 4x minus 12 divided by 19x plus 15. This is a classic rational function here. Now, you want steps, I give you steps. If the inverse exists, the first thing you got to do, step 1, is you're going to need to check to make sure function is what we call 1-to-1. And how do we check to see if the function is 1-to-1? That's called the horizontal line test. So the first thing I'm going to do is I'm going to graph this thing. I'm going to go use my handy dandy calculator over here. Now remember, for a function to tell you, see when you got a function or not, it's called the vertical line test. Vertical lines go up and down. Once you actually have a function, to ensure it's going to be one-to-one, you do a horizontal line test. And a horizontal line can only intersect the function at most one spot. Okay? And the reason why we check this is because only one-to-one functions have inverse functions. If the function is not one-to-one, it doesn't have an inverse function, and that's what we're looking for. We're supposed to be finding inverse functions on this thing. So I'm going to go to y equal and clear out the old graph there. I'm going to type in parentheses 4x minus 12 divided by parentheses 19x plus 15. And I'm going to do a zoom standard, negative 10 by 10 screen there. And this is what I get. I get a graph that looks like this. Somewhere over here at negative 15/19 is a vertical asymptote, and the graph blows up on this side and blows down and goes this way on this side. The question though is it one-to-one? Any horizontal line only intersects the graph at most one spot, so it checks. The answer is yes. If the answer was no, then the answer would be no inverse function exists. Step 2 is change function to y. This is to make it simpler for us, so that gives me y is equal to 4x minus 12 over 19x plus 15. Step number 3, this is the big step right here. This is what you do with inverses. You switch the x and y coordinates. Switch the x and y coordinates. So replace x with y and y with x. So that's going to give me x equals 4y minus 12 over 19y plus 15. And then step number 4, this is the work step, go solve for y. How would you solve for y on this equation? X equals 4y minus 12 over 19y plus 15. Now, your first move is to get rid of fractions. So I would multiply both sides by my common, in this case only denominator. I'll multiply both sides by 19y plus 15. What I do to one side, I do the other. This is going to give me x times 19y plus 15 is equal to here, the 19y plus 15 cancels, you're left with the numerator, 4y minus 12. Next step I would do would be distribute. This gives me 19xy plus 15x is equal to 4y minus 12. I just distribute the x. Keep your eye on the ball. We're trying to solve for who? Y. So get all your y's on one side. So I'm going to subtract 4y from both sides. At the same time, I'm going to subtract 15x from both sides. This is going to give me 19xy minus 4y, this cancels, equals, this cancels, negative 12 minus 15x. So now I've juggled this thing. I've got all my y's on one side, all the terms that don't have y's on the other. I got multiple terms with this y in it. So the trick is factor. So I'm going to factor the y out of this guy, leaving me with 19x minus 4 equals negative 12 minus 15x. And then the last thing I'm going to do to solve for y is divide by both sides by 19x minus 4. End up getting y equals negative 12 minus 15x divided by 19x minus 4. And then there's one last step, step number 5, and that is replace the y with the f inverse of x notation. So the answer is f inverse of x is equal to negative 12 minus 15x divided by 19x minus 4. The inverse function. Same directions on the next one. H of x is equal to e to the 9x plus 3. Find the inverse function if it exists. Well, the first thing I'm going to do is check for one-to-oneness. So I can graph this guy, and when I plug in, let's see here, negative 1/3, here's negative 1/3, I end up getting e to the 0, which is 1. And I know it's an exponential function, so it has this look to it. You can put him on the calculator if you want to. Here's my question. Is it one-to-one? Do the horizontal line test. Horizontal line test should only intersect a one-to-one function in at most one spot. Any horizontal line will intersect at only one spot. So yes, on one-to-one. Step number 2, replace function with y. Y is equal to e to the 9x plus 3. Step number 3, switch the x and y. X is equal to e to the 9y plus 3. Step number 3 is the inverse step. Step number 4 is where the work shows up at. Solve for y. Where's the y located at? It's in the exponent, but he's in the exponent of who? E. And I've got the e guy already by himself, so what kills off e's and brings down exponents at the same time? You want to use the natural log on this thing. So step number 4, I'm going to take the natural log of both sides. So I get the natural log of x is equal to the natural log of e to the 9y plus 3. But e's and natural logs cancel. So I'm left with the natural log of x is equal to 9y plus 3. Solving for y, I would subtract 3. Gives me the natural log of x minus 3 equals 9y. And then I would divide both sides by 9. That gives me y is equal to the natural log of x minus 3 divided by 9. And then step number 5, replace y with the functional notation. What was this function called originally? H of x. So the inverse would be h with a little minus 1. H inverse of x is equal to the natural log of x minus 3 divided by 9. And similarly, last but not least, f of x is equal to the natural log of 13x plus 10. So step number 1, you got to make sure that it's one-to-one. Well, when is this thing equal to 0? At negative 10/13 is where my vertical asymptote is going to be at. And this thing is a log graph, so it's going to shoot straight down on one side and bow out on the other. Question, though, is it one-to-one? One-to-one question mark. Well, any horizontal line only intersects the graph at most one spot. So yes, it is most definitely one-to-one. Step number 2, replace the function with y. Y equals the natural log of 13x plus 10. Step number 3 is switch the x and y. X is equal to the natural log of 13y plus 10. Step number 4, solve for y. You got x equals the natural log of 13y plus 10. I need to get rid of a natural log so I can sit there and solve for that y. What gets rid of natural logs? Basically raising both sides to the power of an e. So you get e to the x is equal to e to the natural log of 13y plus 10. And e raised to the natural log cancels. So I'm left with e to the x is equal to 13y plus 10. Solving for y, I would subtract 10. I get e to the x minus 10 equals 13y. And then I divide both sides by 13, and I get y is equal to e to the x minus 10 divided by 13. And then the last thing I'm going to do is step number 5, which is replace the y with the functional notation. This function was called f of x, so this would be, once again, f inverse of x. That would be equal to e to the x minus 10 divided by 13. Turning functions basically inside out. Does that make sense? Questions? F of x is equal to x cubed plus 1. They want you to find f inverse of x. All right. Here we go. Step 1. F of x is equal to x cubed plus 1. Everybody should know what your classic cubic graph looks like. What does a cubic graph look like? It's a squiggle. So it's a squiggle going from low to high, but plus 1 would shift it up 1 unit. So typically it goes through the origin with shifting it up 1 unit. This is f of x equals x cubed plus 1. Question though is it 1 to 1? Is it 1 to 1? Well, any horizontal line will only intersect the graph at one spot. So the answer is yes. So we go to step number 2. Replace function with y. Y equals x cubed plus 1. Step number 3. This is your big inverse step. Switch the x and y coordinates. X equals y cubed plus 1. Step number 4 is the workhorse. Solve for y. How would you solve for y when you got x equals y cubed plus 1? What's your first move? Subtract 1. Good. So I'm going to get x minus 1 equals y cubed. And then what's your next move to solve for y? What gets rid of a cube? So I'm going to take the cube root of both sides. Cube root, cube root. Cube and the cube root cancel. I'm left with y equals the cube root of x minus 1. And then the last thing I'm going to do here is replace y with the inverse notation. F inverse of x is equal to the cube root of x minus 1. There's my inverse guy. What is part B asking you to do? Because this is a calculus class. And it didn't take us long to leave the calculus, but now we're back again. What is this guy right here? F inverse prime of 2. What do they want me to do? They want me to take the derivative of f inverse. Okay? So f inverse of x is equal to this weird cube root of x minus 1, but I don't do cube roots. What's a cube root also known as? 1/3 power. So this is x minus 1 to the 1/3 power. So f inverse prime of x, the derivative of this guy, what rule would you have to use to take the derivative of x minus 1 raised to the raised to the 1/3 power? Yeah, use chain rule. Derivative of the outside, inside stays the same time derivative of the inside. So chain rule, the 1/3 pops out front. The inside, x minus 1 stays the same, raised to the subtract 1, 1/3 minus 1 is a negative 2/3. Times chain rule, derivative of the outside, inside stays the same time derivative of the inside. What's the derivative of x minus 1 with respect to x? Just 1. So this tells me that f inverse prime of x, when you clean them up, is going to be 1/3 times x minus 1 to the 2/3 power. Negative exponent just goes on the bottom. And then there is part C. What do they want you to do? Find f inverse prime of 2. Well, I got f inverse prime of x, which is 1/x times x minus 1 to the 2/3 power. So if they want me to find f inverse prime of 2, what am I going to do? Because we're still beating to death this functional notation stuff. I'm going to plug in 2 for all my x's. This will be 1/3 times 2 minus 1 to the 2/3 power. This is 1/3 times 2 minus 1 is 1 raised to the 2/3 power. But 1 raised to any power is equal to what? 1. So this is 1 times 3 is 3, so the answer is 1/3. Now, this is what we want you to focus on in problem number 11 here. To find the inverse derivative, you first have to find the inverse function, then take its derivative, and then plug in a number. That was kind of painful. I had 3 parts to this problem here before I can get the derivative evaluated at a particular point. In this case, it was 2. There is a formula for this thing. The derivative of an inverse formula. We cannot find f inverse of x and f of x. When we cannot find f inverse of x and f of x is 1-to-1, then you could use the formula. F inverse prime evaluated at a is the same thing as 1 over f prime evaluated at f inverse of a. So let me show you. They're telling me that f of x is equal to, in this problem, x cubed plus 4x plus 4. Your mission, find f inverse prime of 4. According to the rules, f inverse prime of 4 would be equal to 1 over f prime evaluated at f inverse of 4. To do this problem, you work inside the parentheses first. What is f inverse of 4? Just to remind you, note. F inverse of y is equal to x. Thus, you can always use f of x is equal to y. So here's the deal. If I'm looking for f inverse of 4, the 4 is the y coordinate and we're setting it equal to x. But remember, they got f of x is equal to x cubed plus 4x plus 4. Okay? And remember, y in your function is the same thing. So when they say, what is f inverse of 4, they're telling me the y coordinate. Y is 4. So y is 4, and that's equal to x cubed plus 4x plus 4. You've got to figure out what x is. What's x? Now, you're not supposed to think too deep in this one. It's not an algebraic solve thing. It's one of these things, but look at it. Can you tell me if you've got 4 is equal to x cubed plus 4x plus 4, what does x have to be? And it's a 1-to-1 function, so there's only one answer for this guy. X has got to be 0. Which tells me that f inverse of 4 is going to be equal to 0. Because we're really using the f inverse of y equals x notation. Y was 4, and when I solve for x, I got x to be 0. So now, here we go. To get your answer, this will be 1 over f prime of f inverse of 4. F inverse of 4 is equal to 0. Remember, they gave you f of x, which was equal to x cubed plus 4x plus 4. So what's f prime of x? Now this is regular derivative stuff. So if f of x is equal to x cubed plus 4x plus 4, what's the derivative? 3x squared plus 4. Right. But now what they want is, what is f prime of 0? That would be 3 times 0 squared plus 4, which makes it what? 4. So the answer to my problem, what's f inverse prime of 4? That's equal to 1 over f prime of f inverse of 4. F inverse of 4 was 0, so the answer is 1 over f prime of 0. But f prime of 0 is 4, so the answer is 1/4. 1 over 4. And you look at this thing going, wow, is that any better than what we did before? Yeah, it actually is, because if you look at this function and start trying to find its inverse stuff, you're going to have some nightmares on this thing. But if you remember the coordinate flop switch on the formula, f inverse prime of a is equal to 1 over f prime of f inverse of a, you can still get this thing. So we got another one. Let's do it. F of x is equal to the square root of x cubed plus x squared plus x plus 1. Your mission is to find f inverse prime of 1. But luckily I have the formula memorized. You should too. F inverse prime of a is equal to 1 over f prime of f inverse of a. It just reverses the rules here. F inverse prime of a is equal to 1 over f prime of f inverse of a. So when they want f inverse prime of 1, that's going to be the same thing as 1 over f prime of f inverse of 1. As y equals f of x equals the square root of x cubed plus x squared plus x plus 1, then f inverse of y is equal to x. So when they want f inverse of 1, that's going to be equal to the x coordinate. So remember, y is equal to 1. So when I plug it in, I'm going to get 1 is equal to the square root of x cubed plus x squared plus x plus 1. Now again, you can solve this thing if you really want to, but you're supposed to look at it and tell what does x have to be. It's a one-to-one function, so there's only got to be one answer. What is that? When I take a number and cube it, plus take that same number and square it, plus take that same number and add it to the x squared and the x cubed, and add 1 to it, and then take the square root of it, I get 1. What does that make x equal to? Got to be equal to 0. Because 0 cubed is 0, 0 squared is 0, 0, x is 0. Add all a bunch of zeros together, that's 0 plus 1 is 1, and the square root of 1 is 1. X has got to be 0. So that tells me that f inverse of 1, the y coordinate, is equal to x coordinate, which is 0. So f inverse prime of 1 equals 1 over f prime of f inverse of 1, which will be equal to 1 over f prime of f inverse of 1 is equal to 0. So now all I got to do is find f prime of 0. Well, f of x was equal to x cubed plus x squared plus x plus 1, square root, but I don't do square roots. That's a half power. So what's the derivative of this guy? Well, what rule would I use? Chain rule. Derivative the outside, inside stays the same time derivative the inside. So here we go. Chain rule. This will be equal to 1/2 times x cubed plus x squared plus x plus 1. Derivative the outside raised to the negative 1/2 power. Inside stayed the same, but then times derivative the inside, which is 3x squared plus 2x plus 1. Now you can clean this up, but remember what we're trying to find is f prime of 0. This will be 1/2 times 0 cubed plus 0 squared plus 0 plus 1 raised to the negative 1/2 times 3 times 0 squared plus 2 times 0 plus 1. 0 squared is 0 times 3 is 0. 2 times 0 is 0, so this is 1. 0 cubed is plus 0 squared plus 0 is 0 plus 1 and makes it 1. So this is going to be 1/2 of 1 to the negative 1/2 times 1. Well, 1 to the negative 1/2 is still 1. Times 1 is 1. Times 1/2 is 1/2. So f prime of 0 equals 1/2. Who cares? You do. What was the question? Oh yeah, the question was, what is f inverse prime of 1? By definition, by formula we have memorized, that's 1 over f prime of f inverse of 1. F inverse of 1 was 0 when we calculated it out. And f prime of 0 equals 1/2, so this is 1 over 1/2. And what do you do when you divide by a fraction? Invert and multiply, so the answer is 2. There's the answer. F inverse prime of 1 is actually equal to 2. Now these guys are a little messy, but go back and remember the formula and notice how I'm doing this stuff. This one's a little bit easier as long as you know the formula, because they gave you all the pieces of the puzzle. Suppose f inverse is an inverse function of a differentiable function f, and f of 3 equals 4, f prime of 3 equals 7/4. Then what is f inverse prime of 4? Well, f inverse prime of 4 is the formula f inverse prime of a, which by definition this will be equal to 1 over f prime of f inverse of a, but a is equal to 4. All I did was replace a with 4 and plug it into my formula. Here's the big deal. If f of 3 is equal to 4, then remember with the inverse notation you can write it the other way. This means that 3 is equal to f inverse of 4. So f inverse prime of 4 is equal to 1 over f prime of f inverse of 4. This will be 1 over f prime of f inverse of 4 is actually equal to 3. And what is f prime of 3? Well, they gave that to me. So this is 1 over f prime of 3 is 7/4. And what do you do when you divide by a fraction? Invert multiplies. What's the answer? 4/7. It's 1 over this dude there. More problems here. Here's a WebWork problem that a lot of people just despise because they don't know what to do on this thing. So let me show you the WebWork hint on this one. If, and they're giving you this, the natural log of A is equal to 2, the natural log of B equals 3, and the natural log of C is equal to 5. Your job is to evaluate the natural log of the square root of b to the negative 4, c to the negative 4, a to the negative 3. You're supposed to crunch that sucker out. I don't do square roots, so this will be the natural log of b to the negative 4, c to the negative 4, a to the negative 3, raised to the half a power, because the square root is the half a power. According to log properties, I'm going to try to clean this guy up, because I'm going to try to substitute in for the natural log of b, 3. Substituting in for the natural log of a, I get to plug in 2. And plugging in for the natural log of c, I get 5, which I need to bust this thing up. According to my log properties, where do powers get to go? Out front. So this would be equal to 1/2 the natural log of b to the negative 4, c to the negative 4 times a to the negative 3rd. These guys are being multiplied. According to the log properties, where does multiplication turn into? Addition. But the 1/2 is still out front, so you're going to have to do the 1/2 with a big old bracket here. This in multiplication turns into addition. This will be natural log of b to the negative 4th plus the natural log of c to the negative 4th plus the natural log of a to the negative 3rd. But once again, according to log properties, when I got the natural log of somebody being raised to a power, where do powers get to go? Out front is coefficients. That 1/2 is still out front with the bracket, but in front of the natural log of b to the negative 4, the negative 4 goes. That'll be negative 4b, natural log of b. Plus the natural log of c to the negative 4, the negative 4 goes out front. That'll be negative 4, the natural log of c. Plus here, the natural log of a to the negative 3rd, well, the power, the negative 3 pops out front. It'll be the natural log of a. Now I'm going to distribute my coefficient here of that 1/2. 1/2 of negative 4 is negative 2 times the natural log of b. 1/2 of negative 4 is actually negative 2, natural log of c. Plus a negative is a minus. 1/2 of 3 is actually 3/2 times the natural log of a. All I did was take my old baseball bat and bust this sucker up into multiple terms using my log properties. Now here comes the trick. Now we want to evaluate it. What was the natural log of A equal to? 2. Natural log of B was equal to 3, and natural log of C was equal to 5. So by substitution, this would be negative 2 times the natural log of B was equal to 3, minus 2 times the natural log of C was equal to 5, minus 3 halves the natural log of A was equal to 2. So now all I got to do is clean this thing up. Negative 2 times 3 is negative 6. Minus 2 times 5 is 10. Minus 3 halves times 2. The 2's cancel and left with 3. Minus 6 minus 10 is minus 16. Minus 3 is negative 18. That's my answer. 19. I can't do math. Thank you. 19. Sorry. 19. I can do math there. Negative 6 minus 10 is negative 16. Minus 3 is negative 19. Thank you. There you go. Does that make sense, though? This is what we're after. It's these basically, you're supposed to go up here and use your log properties on this thing and bust them up into multiple terms of single variables here. And then when you got the natural log of B by himself, replace it with 3. Natural log of C, replace it with 5. Natural log of A, replace it with 2. And then you just crunch out your numbers and stuff. Does that make sense? Solve the equations. Well, the first one is actually one of the simpler equations. It's called an exponential equation. Again, classic review. I've got 3 raised to the x minus 4 equals 9. Now, traditionally, when I got a variable in the exponent, the only thing in the world that solves for exponents is logarithms. I want to take the log of this stuff. But be careful. If you can actually rewrite your equation in terms of the same base, when the bases are equal, the exponents have to be equal too. So, take a look at this guy. I got 3 raised to the x minus 4 equals 9. But I can break down 9 in terms of base 3's. What's 9 equal to in terms of base 3's? 3 squared. And here comes the rule. When you have an equation called an exponential equation with variables in the exponent, if you can write the bases to be equal to each other, that would automatically imply that the powers have to be equal to each other. X minus 4 has got to be equal to 2. Now you can go solve for x. Add 4 to both sides. And I end up getting x to be equal to 2 plus 4, which is 6. Does that make sense? Again, if you watch the awesome pre-section video from section 3.1 and 3.2 and all that review stuff I did in the review chapter 3.1, 3.2, this guy over here, I got the natural log of x plus the natural log of x minus 1 equals 4. Your mission? Solve for x. Now, here we go. Now I stole this one off of WebWork, so enjoy this one. This is what I call a log type 1 equation. Now logs on one side equals to a number. So the first thing you want to do with log equations is combine logs. You will notice that the coefficient in front of the logs are 1s. What does addition turn back into when you want to combine logs? Multiplication. So this would be the natural log of x times x minus 1 is equal to 4. You with me? Now, I want to get rid of the natural log. What gets rid of natural logs? What's the property that gets rid of natural logs? E. Raising both sides to e to a power here. So e raised to the natural log of x times x minus 1 is equal to e raised to the 4. What I do to one side, I do to the other. And here, e and natural logs cancel. You're left with x times x minus 1 equals e raised to the 4th power. That should scare most people, but what really is going to scare people is this. Solve for x. Well, I got x times x minus 1. First thing I'm going to do is distribute. This is going to give me x squared minus x is equal to e to the 4th. What kind of equation is this guy? Very good. It is a quadratic. To solve a quadratic, I always set it equal to my favorite number, 0. So I'm going to subtract e to the 4th from both sides. This gives me x squared minus x minus e to the 4th equals 0. Now personally, I would love to come down here and go anti-full factor this thing, but what times what is e to the 4th that differs by 1? Absolutely nothing. Okay, it's not going to factor at all. I got a quadratic that doesn't factor. And I've got to solve this thing. What am I going to do? Quadratic formula. So let's all sing along if we know it. Quadratic formula. The first thing is this. With quadratic formulas, you have to set the equation equals 0. Ax squared plus bx plus c equals 0. And then using the quadratic formula to solve for x, sing along if you know it, it is what? Negative b plus or minus the square root of b squared minus 4ac all over 2a. In our problem here, a is the coefficient in front of the x squared, which is 1. B is the coefficient in front of the x, which is negative 1. C is equal to the constant term, which is the negative e to the 4th. So I'm going to plug it into my formula. X is equal to negative b, which is negative 1, plus or minus the square root of b, which is negative 1 squared minus 4 times a, which is 1 times c, which is negative e to the 4th. All over 2 times a, which is 1. So I get x is equal to negative 1 plus or minus the square root of, let's see here, negative 1 squared is 1. Negative 4 times 1 times negative e to the 4th, that gives you plus 4 e to the 4th. Divided by 2 times 1, which is 2. Ah, yes, it would be. Negative, negative 1. Thank you. Positive 1. Thank you. Got a question for you, though. How many answers are up here? There are 2 answers, that plus or minus. My 2 answers are positive 1, negative, negative 1 makes a positive 1, plus the square root of 1 plus 4 e to the 4th divided by 2. And the other answer is 1 minus the square root of 1 plus 4 e to the 4th divided by 2. And I need to check these guys because this is a logarithmic equation originally. And remember, with log equations, you can't take the log of a negative number. So, plugging this on my handy dandy calculator here, parentheses around my numerator, I've got 1 plus the square root of 1 plus 4e to the 4th, close parentheses for the denominator, over arrow there, close parentheses for the denominator, whole thing divided by 2. I got 7.9059 something brother. And I'm going to recall this thing back down second entry and just change that plus to a minus. And I got negative 6.9059. Negative 6.9059. Now, I do not knock off answers just because they're negative. But I got to go back and plug them back in to check them in the original equation. And when I take negative 6.9 and plug it in, the natural log of negative 6.9 or the natural log of negative 6.9 minus 1, which makes it negative 7.9, I can't take the log of a negative number. This is a violation of rules of math. This is not one of my answers. But 7.9 is good. Natural log of 7.9, that's nice and positive. 7.9 minus 1 is 6.9. That's nice and positive. This is the answer, and there's only one answer. It is 1 plus the square root of 1 plus 4e to the 4th divided by 2. Classic quadratic formula on nasty stuff. Does that make sense? Chapter 3.3. Well, this is a calculus class, so all this stuff in chapter 3.1 and 3.2 is more of memorization. Okay, we did a little limit property stuff here, But now, we're going after the derivatives. Now, I made up these notes and typed up these notes and stuff like that for myself and all the other fellow professors and stuff like that teach this stuff. However, I don't always show all the tricks that I know and give and stuff like that. So, if you'll notice that the way I wrote this thing down, there are 4 derivative formulas that we're going to be discussing in chapter 3.3. That's actually not quite accurate. There are actually 8 of them. But these are the important ones. Okay? So I'm going to come over here and I'm going to rewrite these formulas for section 3.3. Section 3.3, we're talking about derivatives. Here's the deal. Formula number 1. I have y equals e to the x. I'm going to first focus on this guy. This is why this number e, 2.71828 whatever, when you raise it to the x power, shows up in nature naturally. It's one of these God-given numbers. When you actually go out and study science, this e number, 2.718, is like pi. When you study circles, there's a pattern on these things that just show up. E is one of them. And it's not just e, it's the actual e to the x. Because when you take its derivative, the derivative of e to the x is e to the x. It's the only function in the universe, besides 0, it's its own derivative. The derivative of e to the x is e to the x. So when you start studying population growths and models and things grow at a rate proportional to itself stuff, this e to the x pattern shows up. This is where that comes in the nature naturally when you study biology and with microorganisms, or you're studying how many dolphins are in the ocean or whatever the case may be. It follows this exponential pattern. Okay? E to the x. It's its own derivative. But here's the deal. For every rule we give you from this until the end of the semester, there's a rule, and then there's the chain rule version of this rule. That's why I didn't write down the chain rule version of this. I wanted the professors to teach this material to their students. So I'm not just giving you this stuff. You actually have to put this in your notes. So rule number 2 is the chain rule version of it. If I have y equals e, not just to x, but to any other function, y equals e to the function, then you got the chain rule version of this thing. And this really does come from the chain rule here. Chain rule. Derivative outside, inside stays the same time derivative the inside. The inside is the exponential. So derivative e to a function is going to be e to the function, but then you got to do times the derivative of the inside from the chain rule. And the inside is the exponential, so it'll be times the derivative of the exponent. This is the chain rule version of e. Derivative of e to the x is e to the x. Derivative of e to a function is e to the function times the derivative of the exponent. Chain rule version of it. Rule number 3. If you have y is equal a to the x, a, any base, got to be a positive number. Okay, not 1. 1 to the x is kind of stupid because it's just 1. But you could have a fractional base or a base bigger than 1. If you've got a to the x, it is still exponential, so it has the same pattern. The derivative is going to be a to the x, but then because you don't have that magic number e, 2.71828, whatever, you got to multiply by the adjusting factor times the natural log of a. So the derivative of a to the x is a to the x times the natural log of a from the adjusting factor aspect of it, because you didn't have an e. So example, what's the derivative of 5 to the x? It's 5 to the x times natural log of 5. Does that make sense? But for every rule, there's the rule, and then there's the chain rule version of that rule. Rule number 4, chain rule. If y equals a, not just to x, but to a function, I'll call him f of x, a raised to the f of x, Then the derivative is going to be a to that function f of x times the adjusting factor, natural log of a, but then times the derivative of the exponent. This is the chain rule version of that rule. And don't worry, I got lots of examples to play around with this thing. But an easy example would be something like this. What's the derivative of 5 raised to the sine of x? 5 raised to the sine of x. So the function is in the exponent. Sine of x is in the exponent. Well, the derivative is going to be 5 to the sine of x times the natural log of 5 times the derivative of the exponent. What's the derivative of sine of x? Times cosine of x. That would be what its derivative is. Does that make sense? Following the pattern. So, there's 2 exponential versions of this thing, and there's 2 logarithmic versions. Rule number 5. If y is equal to the natural log of x, then the derivative is going to be 1 over x. Derivative natural log of x is 1 over x. They prove this in your textbook, so if you want to see the proof of this using the old limit definition stuff, they actually do it in the textbook. We're just going to go with the rule on this one. The derivative of the natural log of x is 1 over x. So, rule number 6. If y equals chain rule version of it, you got the natural log of a function, then the derivative of this guy is going to be, well, what's the pattern of derivative natural log of x? It's 1 over x. So derivative natural log of a function is going to be 1 over the function, but then you got to do chain rule, times the derivative of the inside, times f prime of x. Now, I know a lot of you guys have had calculus before in high school and stuff. And your teacher probably taught you the derivative of the natural log of a function is f prime of x over f of x. And that's a classic rule. And all they did is clean this guy up. It'll be f prime of x over f of x. But when you write it like that, you kind of forget the pattern of it. What is the pattern on taking the derivative of a natural log of somebody? It's the 1 over. Derivative natural log of x is 1 over x. Derivative natural log of function is 1 over the function. But then chain rule times the derivative of the inside. That's all coming from the chain rule. So this is the chain rule version. Here's the chain rule version. And this is the chain rule version. There's 2 more. Number 7. If you have y equals the log base a of x, you got a log, but it's not the natural log, not that base e guy. Well, you can still take derivative of this dude. Y prime is going to be 1 over x, but then you got to do times 1 over the natural log of a, 1 over the natural log of the adjusting factor. When the exponential is a, you do times the natural log of a. When it's a log base a, you'd multiply by 1 over the natural log of a. The natural log of a is actually in the denominator as your adjusting factor. And then one more. Rule number 8. If y equals the log base a of a function, then y prime is going to be 1 over the function times 1 over the adjusting factor natural log of a, but then chain rule times the derivative of the inside. Chain rule version of this guy. This is the big aspect of section 3.3. And I didn't type this stuff up in all of its glory right at the beginning. I typed up the basic functions, but for every rule, there's the rule and then there's the chain rule version of it. So when you go and watch the awesome pre-section video that some idiot professor made for you guys on this stuff, you will notice that I'm doing a lot of these chain rule versions of these guys, and I got a lot more problems to do, but we'll do those things next time. But before you guys leave, I got a couple minutes left in class. The last thing we got to do is pass back the test. So let me stop here.